Welcome and thanks for joining us today for the fifth webinar, which is part of Pearson Changing Perspective author webinar series. Today, I'm very excited to be facilitating this conversation with one of our market leader author, Roger Freedman. Today's session is called Activating University Physics, Making Physics Lectures Come Alive. For those of you who don't know me, I'm Ajay Bachibi and I'm the Retention Marketing Manager at Pearson and organizer of this author webinar series. Let me briefly introduce our presenter, one of the authors of our market leader title, University Physics with Modern Physics, which now has this 15th edition. Roger Freedman is an associate teaching professor emeritus of physics at the Department of Physics at the University of California, Santa Barbara. He is the co-author of several physics titles like University Physics and College Physics, and he's also a keen pilot, as we could hear. He's also been a letterer for Underground Comics, worked on San Diego Comic-Con in the 70s, and appeared in comics as a supervillain and as a mad scientist, just for a fun fact. We are very excited that you could join us today, Roger. Just a quick thank you for my colleague in the background who are making sure that the webinar runs smoothly. And before we start, a little housekeeping. We know many of you are working from home, and as you know, from these kinds of conversation, we sometimes get some background noises. So if you could please make sure you are on mute to ensure everyone gets the opportunity to hear from our presenters. We have a packed agenda and a lot to get through over the next hour. But firstly, we would like to thank those who have pre-submitted questions. We will try to incorporate these questions into the agenda to make sure they are covered. However, as always, we'd like this to be an interactive and engaging session as much as possible. So please feel free to ask any questions you may have in the chat, and we'll try to answer them on the go or come off mute in the Q&A session after the presentation. The recording will be shared with you later after the presentation in about a week's time. If you're interested in getting a sample copy or a demo of the author's work, we will be in touch with you soon after the webinar on how to do that. So once again, please feel free to use the chat function while the professor is giving his presentation, and we will try to answer them either on the go or after the presentation. Okay, so that's all from me now. I will pass things over to Roger.
Great, well, thanks very much. And thank you all for being here today. I really appreciate it. Let me bring this alive. So as advertised, I'm going to be talking about activating university physics and making physics lectures come alive. So I'm not just going to be talking about the book. I'll also be talking about some techniques that I use in the classroom that I've actually found to be extraordinarily helpful and actually help students make better use of the textbook. And also at the end, I'll be telling you about a brand new book project that's actually associated with university physics, a sample chapter which I'll make available to you at the end of the talk today. So again, as you were told before, please feel free to ask any and all questions in the chat during the webinar, and we'll get to as many of those as we can. So as mentioned, I'm the co-author on the university physics textbook with the late Hugh Young. The book actually has a long history. First edition came out in 1948. The first edition came out before I came out. But so it's really been an adventure and a privilege to be involved with that and to see the book show up not just in English, but also in Spanish, in Thai, and a variety of other languages. So it's really been a great experience to have sort of a global influence on physics education. One thing that I have noticed that seems to be very universal from no matter what country the students are using the book or trying to study physics is they all have kind of the same complaints. And one of the standard complaints that you hear from students, and certainly I hear it, and I know you all have heard it as well, is this statement that, I really understand the concepts because I have such a good instructor, as all your students tell you, but I just can't do the problems. Very common complaint. And the question is, what can we do about that? And certainly that's something we all struggle with. I'll talk about some of the features in the book that are designed to deal with that, but the key thing that I find is a major factor with that is actually the way that we teach. And the fact is, most of us to this day, even after going through the pandemic, most of us still lecture. If we have a blackboard, we stand in front of it. If we have a PowerPoint slides, as I'm doing now, we just sort of step through it. But most of what we do is in the form of a lecture. And you might ask the question, well, why is it that we lecture? And fundamentally, the reason why we lecture in physics class is because that's what our professors did for us. And the reason that our professors did that for us is because that's what their professors did for them. And you can go further back up the chain, and eventually you'll find yourself back in the Middle Ages. This is one of my favorite paintings. This is by a painter named Laurentius de Voltolina. This is the University of Bologna in Italy in the late 14th century. And the gentleman up there at the podium is Henricus the German. So I believe he's actually a lecturer in the Faculty of Medicine. And what I love about this picture, not only does it show that the shape of our lecture halls hasn't changed very much in centuries, but also shows what actually happens during most lectures. So just like today, there's a guy with a beard up at the front of the classroom telling you what's going on. The dress code was much better back then, by the way. And if you look in the front row, everyone's paying really close attention. But you get to the second row and you get some people who are just kind of, talking to each other, trying to do a chat. You get to the third row, there's someone over there who in the front row, closest to us, clearly had way too much fun partying last night. A couple of people talking to each other. The person up against the wall, I think, is updating their Instagram profile. You get to the back row and they're pretty much completely tuned out of what's happening in the lecture. And the reason this is happening is that the question is, why were these people lecturing? Why were they sitting in lecture? It's because you're looking at an age before the invention of the printing press. So the professor up at the front of the classroom, he has a copy of the book engrossed by monks from some ancient Latin text, and he's reading it to the students. Remember, in French, une lecture is just a reading. And he's reading to the students so they can copy down and get their very own copy of what's in the book. Well, we have the printing press now, we have the internet and so on. The question is, why do we continue to do this sort of stuff? You might ask, well, okay, it's an old-fashioned way of doing it, but we've been doing it for centuries, so it must be the best way, right? Well, one way we can measure that is actually to try to do some quantitative analysis of how much students actually learn in an intro physics class. And a great way to do that is by calculating for a given class what the class learning gain is. The idea here is you give the students a standardized test, say to test their conceptual understanding of physics, and you give them the test before they've been instructed. Then you give them the same test sometime later after they've been instructed. And you'd like to see how much improvement have you had. And so the quantity that's done is called the normalized gain, or little g. And we have to have one equation in a physics talk after all. And you take, in the numerator, you have the pre-test average as a percentage, and you subtract that from the post-test average. You hope the numerator will be a positive number because there's been some improvement. And to normalize that, you divide by 100% minus the pre-test percentage. So think what that would mean. If the students learned absolutely nothing, the post-test and pre-test values would be the same, and the numerator would be 0 and the gain would be 0. If the students had perfect understanding after instruction, the post-test percentage would be 100, the numerator and the denominator would be the same, and G would be equal to 1. So those are our limits. G equals 0 means no learning, G equals 1 means perfect learning. So what do the results actually look like for a variety of intro physics classes? So here's some actual data. And what you see on the vertical axis is the fraction of courses that were looked at in this survey. And on the horizontal axis is the actual value of that learning gain, little g, with larger values to the right. So notice no one's gotten to 100%, but there's some class over there with like 0.68. So the students are basically 2/3 of the way to perfect understanding. Over on the left are these very disappointing numbers like 0.12. The students are basically getting 1/8 of the possible amount of learning they could get. It's like, well, I'd sure like to be over on the right-hand side with those green bars, but what's the difference between the red and the green ones here? And the difference is the ones that are in red are called, those are ones where there was a standard lecture. And awesome professors standing in front of the class doing a lecture in the same fashion that we've done since the 14th century. And the disappointing thing about that is you'll notice that the learning gain of that, it maxes out at something like 0.28. So the students are only learning a quarter of what they could learn in potentially. The green ones look much better. What are the green ones? Those are the ones where there's active learning taking place. So good question. Okay, so what is active learning? Clearly it has a better result than standard lecture, but what is it and how do I make it happen? So let's talk about active learning a little bit, which, as this data shows, is actually rather more effective. And in fact, in the set of links that I'll give you at the end of the talk, there's a wonderful survey article where they've looked at the same effect, not just in physics, but across science, engineering, and mathematics, and have found you get exactly the same results, dramatic improvement with using this active learning technique. The question is, what is it? And so really our question is, what is active learning and how do we make it happen? And as the name suggests, what that means, your students are going to be actively engaged during the class period. As opposed to sitting passively during a lecture, they're actually doing something that's very active as much as possible throughout the entire time that you're meeting with them. Among other things, that means you're getting the students to answer conceptual questions. You're posing questions to students and encouraging them to actually consult with their neighbors and figure out what the correct answer is. You're having them predict the results of experiments. We all do demonstrations in our physics classes, and instead of just simply showing them the demonstration, an excellent thing to do is to ask them to consult with their neighbors and predict what the result of the experiment will be. And you can also have them actually solve problems. You can take problems from out of the textbook and either give them a whole problem or give them a portion of a problem to work on and wander around the classroom and see what kind of effect what kind of results they're actually getting, get some understanding of what their difficulties are, and try to help them out with that. I want to concentrate in the short time we have here on that first of the three, the notion of using your class time to have the students answer conceptual questions. And so what kind of questions are we talking about, and where can I find those? So, and the reason I want to emphasize concepts is, remember we said students saying, oh, I understand the concepts, I just can't do the problems. Well, if you actually look closely at what they say, if you take what they're saying and you interview them more closely, if you run it through the universal translator and ask, what are they really saying? What they're really saying is not that they understand the concepts and therefore they cannot do the problems. What they're really saying is, I can do the problems that are exactly like the ones in the worked examples of the book. If it's just like that and I just have to change the numbers or it's a slightly different, I can kind of do that. But I don't understand the concepts well enough to really do anything else. So fundamentally, that conceptual understanding is at the basis of everything. And so if the students don't have that deep conceptual understanding, then all they're doing in problems is moving around symbols and numbers on a piece of paper. And that's not a very effective thing for physics students to learn how to do. So that conceptual understanding really underpins everything. So that's why it's important to spend time making sure they really have that conceptual understanding. So what kind of questions are we talking about here? And so a great tool that actually helps students with conceptual understanding are what are called clicker questions. And the name clicker is kind of an odd one. These questions were originally developed for use with so-called classroom response systems, where the students may have either a physical device or device on their cell phones where they can respond to questions in class, and the professor can actually then see what the results are like. And they're called clickers, those devices, because when you push the button on them, it makes no clicking sound whatsoever. It's a very strange name, but nonetheless, they're referred to generically as clicker questions. And you don't have to use any technology at all. I know people who very effectively are able to do this just by telling students hold up one finger for A, two fingers for B, and so on. And that way you get a good sense from your students of how they're responding. Let's take a look at some of these questions, ones that I've actually used in my physics classes to get a sense of what these are like. So here's one. So I'll just let you read this for a second and think to yourself what the answer to this question might be. So let's take, say, a minute just to do that, and I'll shut up and let you think about the question. Okay, we had about 60 seconds there. And if I was doing this with actual students, I'd give them a while to a somewhat longer time to do this. And I would tell them, discuss with your neighbors, see if you can come to a consensus to what the right answer is. But this is obviously a highly educated group. And I'm sure just about all of you figured out without working very hard at all, is that the correct answer is C, namely that point at the very top of the string at point A, there the velocity is 0. As the wave's been passing through, that's where this thing has reached its actual maximum height and is about to start heading back down. The bar graph you see there is the actual data from my class on what their results are like. And this is a class of about 200 students. And happily, you can see 90% of the students gave the correct answer. So you might look at that and say, okay, so clearly the students understand what's happening with motion of wave on a string, no problem. Well, in the same fashion that when you go to a dentist, if the dentist kind of pokes that little sharp thing into the gum one place and you don't scream, they might say your gums are okay, but they'll probably say, no, I'm going to push a little harder and see what happens. And so let's push a little harder. Let's do a follow-up question about the same motion. So here's a follow-up question. Take another minute to read this one and see if you can guess what the correct answer is, and also see if you can guess what the most common answer that students gave might have been. Okay, well, you had about a minute to answer that one. And as physicists, we can look at this and say, okay, what's currently happening is the wave is moving to the right, as described in the problem statement. And so that point at the point labeled x equals b, there the wave right there, the displacement is 0, but you can see that wave crest is coming along. So clearly that point at b is going to start moving upward. So the correct answer should be A. And that is the correct answer, but 3/4 of my students said the correct answer was B. So even though that first question might have said, oh, the students understand what's happening here, here it's clear they did not. And so the real question is, why did so many students give the incorrect answer? What were they thinking? And so at this point, what I actually would do in the class is say, okay, well, I was pleased to see that a fifth of the class got the right answer, but what's really going on with the other answer? So I will ask students, okay, how did you vote and why did you vote that way? And in talking to students, what I found, most of them said, well, it's clear that at point B, there's a downward slope to the curve. And we learned that slope is related to velocity. So a downward slope means a negative velocity, right? Well, clearly what's happening there, the students are confusing a graph of displacement versus position, which is what we see here in this snapshot of the wave, with the graph of displacement versus time. And so, yes, they had the idea that slope is related to velocity, but that doesn't apply to what we're seeing in this illustration here. So having follow-up questions like this can be incredibly helpful, really give you a chance to diagnose what the student's confusion is like. And so clearly they realize, if you've gone through that discussion, and this certainly takes time in the classroom to do it, but after that, the students, okay, now I understand the difference in these two kinds of graphs, y versus x, y versus t, and that will help them tremendously going forward. So again, getting that right conceptual understanding is much more important, I think, than just being able to push numbers around on a piece of paper. In addition to multiple choice questions like this, I also do some ranking task questions. I won't actually ask you to go through this one. This takes maybe a little more time than we have, but here I've shown them 3 different orbits of a spacecraft going around the Earth, and I asked them to rank them in terms of what's the angular momentum of those orbits. And that'll take a little bit of thinking. The cool thing with this is not just picking out one particular answer, because if you have a multiple choice question, you have 1 chance in 5 of getting it right. Here I have 3 things, so I have 3 factorial or 6 different possibilities for what the answer could be. The ranking turns out to be B, C, A in this case. And if I had, say, 4 things to rank, then it's 4 factorial different options. And so the students really have to think in a somewhat different fashion to do these kind of ranking task questions. And say, well, okay, well, these questions are great. They're kind of fun to deal with. And the real question is, what do I get out of doing this? So what active learning really provides is it provides feedback, and actually provides 3 different kinds of feedback. So one is student to student feedback. As I said, during the classroom, when I pose one of these questions, I tell the students, talk to each other, figure out what the correct answer is. It's really amazing in a class of, I teach class with up to 300 students. And when you have 300 students all actually talking about physics, it's a pretty exciting place to be. So they interact with each other and they share ideas with each other, which is really very impressive. They also give me immediate feedback as to what they understand, what they don't understand. For that second multiple choice question, when I saw that only 1 in 5 students was getting the correct answer, it says, okay, there's something here they don't quite understand, and I need to figure out what that is. And I might not have guessed in advance what that point of confusion was, but that problem sort of brought it out for me. And because I learned that in real time as to what the students are confused about, I can give them feedback in real time, that instructor to student feedback, as to what they can do to improve their understanding and how to avoid making mistakes like that going forward. So it really turns the classroom into a very active and a very dynamic sort of place. Now you might wonder, okay, well, these clicker questions are great, but where can I find them? And probably more importantly, where can I find the answers to these? Well, you do not need to hire a detective agency to do this, I'm happy to report. Instead, you'll actually find them associated with the textbook and in the online supplement called Mastering Physics. Mastering Physics is both an online homework system, which is really awesome and actually developed in-house at MIT a number of years ago, but also has a tremendous resource for all kinds of other stuff, including all these clicker questions. So if you log into Mastering Physics for university physics, for every chapter, you'll find a set of clicker questions. And I think the clicker questions are pretty good, but I say that only because I wrote them. But you'll find an extensive set of those for every chapter, all of the 44 chapters in the book. And there's also lots of other sources for clicker questions you can find online as well. So there's no need to write those things yourself. You can just download them. And if you don't like the way they're written, they're all completely editable. And so you can change them and use them however you see fit. As I said, Mastering Physics has a bunch of other stuff besides those clicker questions. One question I get from a lot of instructors, particularly through the pandemic and in the post-pandemic era, which is, what kind of videos do you have? And in fact, Mastering Physics has a very extensive video content associated with it, almost more than you can list. There are these video tutor solutions where you literally have someone leading you through solving each of the worked examples in the book, which is really quite amazing. There's demonstrations of different actual physics experimental demonstrations, which have this pause and predict feature. Well, they'll pause at a certain point and ask the student to predict what's going to happen next when they actually do the experiment. There's an extensive set of conceptual videos dealing with very simple concepts in physics. And probably the coolest is my colleague Matt Anderson at San Diego State University in California has a very extensive set of short video lectures. There's literally hundreds of these associated with the book, and they're all available for student use. In fact, one question I often get about active learning, about spending all that time in the classroom on those clicker questions and other exercises, how are you going to have time to actually talk about what's in the book? And I always say, if there's anything more boring than having a professor just read for you what's in the book, it's probably having the guy who wrote the book just read for you what's in the book. That's incredibly boring. You don't want to do that. So what I do instead is I actually, instead of spending that lecture time on actually lecturing, I use these video lectures to replace, in my case, pretty much all of my own lectures, and I free up class time for active learning. And the great thing with active learning is, unlike what we saw in that medieval painting, is the students are all engaged. No one has time to fall asleep, but they all have time to sit there and think about physics and actually learn in real time, get feedback from each other, get feedback from me, and have them give feedback to me that I can use to better help them with this process of learning physics, learning the concepts, they can better solve the problems. So again, lots of tools associated with the Mastering Physics to help you out with active learning. And I'm happy to say there's also a bunch of features in the textbook that are designed to help students with learning as well. So I'll just spend a few minutes talking about those. And so one is actually visual aids to learning. As you heard at the beginning of the talk, I sort of have a long history with comic books. Certainly grew up reading them. Was involved with starting San Diego Comic-Con back in the beginning in the early 1970s. After on the 50th anniversary, I actually got the golden ticket, so I can now just show up at the door and get into Comic-Con every year, and be in there with 135,000 of my closest friends. But comic books are actually give you a lot of instructional ideas as to what works for teaching. And what do I mean by that? Let me show you an example. Here's actually a couple of panels from a famous comic book that's an early issue of Spider-Man from 1963. And you notice I blacked out what's in the word balloons. So you can tell there's something happening here. Clearly, there's something happening to the character Peter Parker as the Amazing Spider-Man, but without the captions, it's a little hard to tell what the story is. But if you put the captions back in the word balloons, and okay, now I can see what he's thinking about. You get a little sense of what the story is about. You know how the story is supposed to proceed from here. And so clearly those captions are very useful. Well, we actually use that same concept in university physics. So for instance, here's a pretty standard key equation you'll see in every physics textbook, and we all recognize this is Newton's third law. It says the force that object A exerts on object B is the negative of the force that B exerts on A. Same magnitude, opposite direction. But that's a little abstract, isn't it? And it's a little bit like that Spider-Man panels with no captions with it. So what we do in university physics is we present the equation like this. Exact same equation, but notice what we've added. We've added the equivalent to putting on those word balloons. And so we're describing what the equation is actually telling you and giving you some interpretation of what this actually means. And you'll find that for all of the key equations throughout university physics, using that sort of comic book-like captioning to really help students understand what's going on. You'll find that same kind of annotations, by the way, not just on equations, but also on most of the figures, with helping students understand what the figures are really saying, and adding a textual component to help them better understand the graphical component associated with the figures themselves. The buzzword you'll find among the education folks is this is multiple representations of the same idea, and having those multiple representations is actually a tremendous help. We also, in the book, as I mentioned earlier, the main complaint that students have is I can't do the problem. So, okay, let's give you as much help as we can with actually how to solve problems. Not just specific types of problems, but how to solve problems generically. And we actually have a rubric that we use throughout the book, which in English, the acronym is IC, which is the steps you go through in solving any problem is identifying what kind of problem is it. So for instance, does this involve momentum? Does this involve energy? Does this involve kinematics? What kind of problem is it? There's setting up the problem, deciding, okay, what am I trying to find? What's my target variable? What are the key equations I'm going to use? Basically, what are the tools I need to take down from the workbench in order to solve the problem? There's the execute part, the one where you actually do the math and try to figure out what the answer is. And probably most important at the end, E is evaluate. Look at the answer, say, what is this telling me? Does this answer make sense? Are the units correct? And also physically, what does this mean? If this says, for instance, that the kinetic energy depends on the square of the speed, what does that tell me in terms of if I double the speed, how's it going to change the kinetic energy, and ideas like that. And we use that throughout the book. For instance, in every chapter, you'll find these problem-solving strategies that give students guidance as to how to solve particular classes of problems. So here's, for instance, a strategy about how to solve problems that involves sound intensity. And you'll notice we use that same rubric in the strategy itself. It begins with identifying, set up, execute, and evaluate. And you also see that in all the worked examples. For instance, here's an example from that same chapter about intensity. We begin by saying identify and set up what kind of problem this is, do the actual execution, do the mathematics, and then evaluate it to see what's going on. And you'll notice there's a couple other features in these worked examples as well. One is we talk about, we mentioned what is the key concept. At the beginning of each chapter is a list of the concepts that you need that you'll actually learn about in the course of the chapter. And here we illustrate these and say, okay, for this problem, what was the concept that we used? And what's your message that you should take away from this worked example. You also notice there's a reference here to what are called variation problems. And in every chapter, we pick out 3 examples and we add so-called variation problems to those. And those variation problems are basically, as the name suggests, variations on a theme. They're similar to the problem in this example, but each variation, the first, second, and third, is slightly more removed from that original example. And so you're helping students, essentially scaffolding them with being able to solve problems on their own, taking them step by step further away from this worked example where they can see all the details to figure out how to do it themselves. And so, for instance, here for that example I just showed you, here are a set of, in this case, actually we have 4 variation problems that we added for this one. And each one is a little more different than what was in the worked example. And to help the students out, the answers for each of those are given at the end of the chapter. So really helping students out again with this whole issue of how to solve problems by giving them some guided practice in that fashion. Also, at the end of each chapter, you'll find a bridging problem that helps students sort of transition to doing the quote real problems that you'll find at the end of the chapter. And this one, again, you'll notice use that same identify, set up, execute, evaluate steps that we talked about earlier. And in this case, tells the students step by step, here's what you got to do. And so again, it's modeling proper problem solving techniques so that they can then go ahead and use those ideas for their own problem solving on their own, where they're literally, in that case, working without assistance. And again, you notice here, modeling that same identify, set up, execute, evaluate. And the answers for all these are provided at the end of the chapter as well. One really important thing that we want to do is to actually confront misconceptions. Most physics books will tell you what the right answer is. What most physics books do not do is tell you what the wrong answers are that many students come up with, and in particular, why they're wrong. And those things are incorrect, very robust and very deeply ingrained in a lot of students. And the reason is when your students first come to take a university physics class, the problem is they're already experts in physics. How can that be? Well, it's because by that point, they've had at least 18 years of doing things like running and jumping, throwing balls, catching balls, turning light switches on and off. And so they built up in their head a set of, quote, common sense, unquote, ideas about what the physical universe is like. And unfortunately, most of these ideas turned out to be incorrect. So for instance, if you ask an untutored students, okay, a car runs into a wall and the car stops, why did it stop? What we would like to say is, well, the car pushes on the wall. By Newton's third law, the wall pushes back on the car with that same, an equally strong force in the opposite direction. And it's a force exerted by the wall that'll stop the car. If you ask that untutored students, well, why does the wall stop the car? They'll give you a much simpler answer. They say, well, the wall got in the way. Well, yes, but that's not really the answer we're looking for. And so they have some very different notions of what the physical universe is like. And so, and in fact, much of that idea turns out to be more Aristotelian than it does Newtonian. And so you have to deal with it. And so that's why we have caution paragraphs in every chapter of the textbook. And these caution paragraphs point out a couple different kinds of misconception. On one hand, they point out common points of confusion. For instance, here's one about waves on a string or waves in a medium. Talking about, don't confuse the velocity of the wave as a whole moving through space with the velocity of individual particles within the medium that's carrying the wave. And also pointing out common preconceptions. For instance, the word acceleration, for most people, this means speeding up. But in physics, of course, that can mean either speeding up, slowing down, or turning. Anything that changes the velocity vector counts as an acceleration. And so here we point that out very explicitly. In many books, you just say, well, here's the definition of acceleration, deal with it. But here we really confront students with, you're probably having some misconception with this, and we're going to help you out with that. As it turns out, those ideas of confronting misconceptions are certainly not new to our book, nor is it particularly recent, but it is something I actually encountered as a young person, which is, as I mentioned from reading comics, some of the comic books I read actually included features like this one. There's this wonderful feature from DC Comics in the 50s and 60s called Science Says You're Wrong If You Believe That. This is one about understanding the time it takes for a bullet to fall to the ground if it's dropped compared to the time it would take if it's fired horizontally. And with no air resistance, those two times are the same. Also, you actually confront the idea that the moon revolves around the Earth. And in fact, the Earth and the moon both orbit around their common center of mass. So pretty cool stuff for a young kid to see. And the idea stuck with me for these caution paragraphs that you see in today's university physics. These actually, by the way, showed up in a couple of my favorite comic titles, Strange Adventures and Mystery in Space from DC Comics back in the early 1960s. And that actually taught me that the comic medium can actually be very, not only entertaining, but also very useful for educational purposes. And that's actually related to the latest project that I'm working on, a supplement to university physics, which is actually a comic book. And it's a physics comic book designed not to completely cover every subject that you'd find in university physics, but to pick out what are some of the topics that students find most challenging, and how can we help them with better solving problems that involve those concepts. And so, and this is actually a collaboration I'm doing with my good friend Juanele, which, to the relief of everyone who's not a Spanish speaker, his full name is Juan Manuel Ramirez de Arellano Niño Rincon, and we're all very relieved that he just goes by Juanele for short. But he's both a professional cartoonist and he's a physics professor at Tec de Monterrey, the largest private university system in Mexico, at their Mexico City campus. And so he's really the perfect collaborator for this, as well as a superb artist. I'll just tell you a little bit about the comic, and I'll give you a link at the end for actually how you can download a sample chapter of this. And so our characters are a somewhat befuddled beginning student named Alonzo, a more experienced student, Elena, who's able to help Alonzo out. There's Elena's pet cat, Kepler, who actually knows a remarkable amount of physics for a cat. And then there's a squirrel who knows a fair amount of physics as well, and sometimes helpful, sometimes just plain annoying, as squirrels will sometimes be. You notice there's no professors in this. This is just students interacting with each other. And so it makes it a much friendlier experience for the students. So Alonzo, like any typical student, will actually have lots of difficulties. Here he's actually confused about what to do with a block on an inclined plane. Which way does the friction force point? Does it matter whether it's sliding? Does it matter whether it's at rest? How do I figure out what the direction of the force is? And Elena and Kepler actually help out with a lot of that. And so she's providing that kind of student-to-student feedback that I talked about before in the context of active learning. And so by doing this in a friendly fashion, using cute characters and so on, is actually very helpful. And our experience with students who've used this has said that, yeah, this is really a fun and entertaining way to learn stuff. We pose conceptual questions, much like the clicker question that we saw earlier. This is one about if you're on a horizontal surface versus a tilted surface, in which case is the kinetic friction force greater? All else being the same, how does that angle actually affect the magnitude of the friction force? And we go through the answers, and actually Kepler for cat is remarkably good at doing algebra, and so leads you through all the explanations on this. And so again, doing it in a very step-by-step fashion, leading you through all the steps, much like you might do at the blackboard with an individual student. Here, that job is taken over by these very relatable sort of cartoon characters. And we don't just do conceptual problems, we also do full-on physics problems. Here's a question about what's the maximum angle to prevent our characters from sliding down the ramp, given the coefficients of friction and the masses and all that. And so the class all work together with this, excuse me, and go through all the steps. Takes several pages of the comic to make this happen. Excuse me a second. My apologies. So really lots of this step-by-step help. Same sort of thing you could actually do with a student with Blackboard, but here it's done in a really easy to read and step-by-step fashion, and with beautiful illustrations on that end. And just like as we saw with the IC problem-solving strategy, here we're careful to point out that getting the answer is not just a matter of getting the numerical values. Here we're figuring out what's the acceleration of our cat and squirrel as they're sliding on a ramp, either going downhill on the left or uphill on the right, figuring out what the acceleration must be, but it's also interpreting those results and understanding why you get different results in the two cases. So again, we're modeling good problem-solving practice through these the interactions of our characters in the physics comic book. And since Juanete is, of course, in Mexico City, and the book is used extensively in Spanish translation, every chapter of the book will also be available, not just in English, but also in Spanish as well. So it's actually been fun for me because unlike a typical physics textbook, here we actually put in jokes. And the challenge for me is to come up with jokes that'll work just as well in English as they will in Spanish. So I'll end it there. I'm sorry, go ahead.
Sorry, there is a question from one of the
Yeah.
participants. Did you also
Sure.
include examples of the friction force on a car driving slowly uphill?
Not for this one, no. Here we were just doing sliding and static friction. So we were just doing blocks in an inclined plane. So in the comic book, that the answer is no. We have not done anything involving rolling friction.
Okay, thank you.
Yeah. Well, that actually brings us to the end of what I wanted to talk about. So please feel free to contact me by email with any questions you might have on all this stuff. But as I did say, I did want to give you a link to, I put together a document that has a lot more information about active learning, as well as sample chapters of this comic book in both English and Spanish. And also, I know some folks had some questions about dealing with ChatGPT, and there's a cool link I have included in there as well. So you can either scan that with your mobile device and go directly to that page here. And I've also put in the link that'll take you directly to that. So I will end things there. Thank you for your attention, and we'll throw the floor open to questions.
Well, if you have any questions, please feel free to come off mute or type in your questions in the chat box. We already have some pre-submitted questions, but I just would like to wait for you to.
Oh, hi, Anne-Marie.
Hi, Roger. I just wanted to comment about the friction on a car driving uphill for various reasons, because I've used that with students, and they typically draw a friction force downhill because that's what they are used to doing.
Oh, yeah, yeah.
And they add an engine force, which doesn't act on the car, it's within the car.
Exactly. No, that whole issue of dealing with what direction is the friction force when you're rolling.
Yeah, well, it's still static friction, except that it's internal energy. The energy conversion is internal, which is tricky.
Exactly. Yes. Yeah, but the whole so what we've done with the comic book is really dealing with sort of the first time they encounter friction, where they're just translational motion, and if you add the rotational motion later on, that adds an additional level of madness to the students, I find. Yeah.
Well, on the other hand, they have encountered friction their whole life, so you might want to make use of that.
Yes, that's true. Yeah, and we certainly do later on when we. It's actually in chapter 10 that we get to the whole business of friction on an object that's rolling. Yeah, so we certainly do encounter that as well. But you're right that that whole notion of of dealing with all this everyday experience is challenging, to say the least.
I had an example with it was a physics competition in Sweden, and it was a question of an accelerating car, and in the introduction they had said that they should draw figures, but they didn't say that for the problem itself. So when we graded it, the other teachers, it doesn't matter, they didn't say. So it was very few who draw figures, and a minority of them got it right. So I mean, it's a useful exercise somehow or other.
Yes, exactly. No, and this comes back to what I was saying before about doing multiple representations of the same thing. You really need to have students in their answers to any problem include those kind of graphical representations and something other than just equations or just text. That, by the way, is one really good way to get around any of these issues with ChatGPT, which is if you're asked the students to include a diagram of what's going on, ChatGPT does a really crappy job of doing diagrams.
Well, it's pretty crappy with acceleration and forces. It's quite good at reproducing student misconceptions.
Yes, yeah. In fact, one interesting recommendation I'd seen that what you can do with ChatGPT is have ChatGPT come up with an answer to a problem, and then have your students pick apart why that answer is incorrect.
Yeah.
Okay, thank you, Anne-Marie, for your input.
And just for the background, Anne-Marie and I were postdocs at the University of Washington.
Not quite 100 years ago, but nearly.
Let's just say in the last century, yes. process.
Yeah.
That's lovely. Does anyone else have any questions? Please come off mute, or I will just ask the pre-submitted questions. Okay, so maybe I will just ask those questions from you. So the first question is, I learned physics perfectly well from lectures. Why is it necessary to change my technique to use an active learning?
Exactly. That's a very good question. And it's certainly true that many of us think we learn perfectly well from lectures. But you have to remember that, think of all the people who were in your introductory physics class and think how few of them are now today physics professors. Basically, the reason you got to where you are is because you were able to survive the whole lecture process. By contrast, by using the active learning technique, there's a couple of advantages. One, it's a heck of a lot more fun. I find in class, the students do most of the talking, so I'm less likely to get hoarse and have to drink something in the middle of the class. And secondly, there's actually lots of research which indicates that not only does it give you improved learning gain for the students, it also tends to have an even greater effect on groups of students who traditionally did not do so well in an intro physics class. It lifts them up to the same level as everyone else, and it also reduces the failure rate, reduces the rate at which students will leave the so-called STEM pipeline and go do something else. They said, this is too hard, I can't handle this. I thought I was interested in this in high school and I can't handle it now. And so there's actually lots of advantages. And frankly, it's so much more fun than lecturing that I would never consider actually going back to doing a straight lecture. And to be honest, today, two of the most fun minutes during today's presentation was when I wasn't saying anything, but you guys were actually thinking about those conceptual questions. In a real class, it would have been even more fun because I would have heard everyone talking with each other and literally hear the smoke coming from people's ears. They were thinking about what's going on. So it really dramatically changes what the classroom is like and makes it so much more entertaining. So not only is it more entertaining, but as I say, it's pedagogically much more useful. Yes, there was some of us who were able to succeed with lecturing, but we're the exception. We're several sigma away from the mean.
I totally agree. When that particular spark comes out of from students, when they realize they understand, that's a really precious moment, isn't it? And actually they learn a lot from each other too, so
yes.
It's not only the lecturer who gives them the knowledge.
Yeah, yeah, and actually on that issue of students learning from each other, think of all the times that you as an instructor have been trying to explain something to a colleague or to a student, and in the process of explaining, you say, oh wait, okay, now I understand how that works. Because by explaining to someone else, you finally got some insight on what was happening. Well, the exact thing happens with the students. When they have to explain something to someone else, it changes the way they interact with the material, gives them better insight. What's interesting as well, as I mentioned, when I give these clicker questions in class, I will go around and I will just point to students and say, okay, how did you vote, and tell the class why. And I find that typically the students who give the correct answer are able to better verbalize why it's correct than the students who give the incorrect answer, who tend to waffle a little bit more. And you might think, well, that must be intimidating for students to have to speak in front of a group of several hundred students. And it is. So I actually have a reward system. When I teach these classes, I carry a bag of the little fun-sized candies. And if I call on you and make you talk in class, you get a piece of candy. So there is a reward system associated with this as well.
I really want to attend one of your classes. Okay, maybe we can move on to some other questions. And there are two very similar questions which have been pre-submitted. One of them is, what are some strategies to prevent students from using ChatGPT to solve their physics problems? And the other question is, how do we reconfigure coursework assignments effectively with the dawn of AI like ChatGPT?
Sure, okay. The best, and really the same answer deals with both of those. ChatGPT will only be a problem if you're giving really simple type problems. Like, okay, here's this problem. What's a number? What's the numerical answer? Or repeat back something that's in the textbook. So if you're giving questions at sort of that lowest level of understanding, yes, that is something where ChatGPT could potentially get in the way. So instead, some good advice I've seen is one is just make students explain their work. And ChatGPT does a great job of putting out this long string of words that sound like they mean something, but on closer inspection do not. Obviously, it's getting better from by day to day, but fundamentally it works by copying other people and trying to put that stuff together. If you give them assignments that no one has given before, even if it's a matter of taking an end of chapter problem from university physics and modifying a little bit, then that does a tremendous amount of getting away from the problem. ChatGPT, as I mentioned, can't do images. It can't do diagrams. So tell students, I want to see your figures on this. Give me a graph of the answers. So for instance, the one problem we had in the comic book, you're having students figure out what's the maximum angle, the angle of repose at which you could have place our two characters on a ramp so they don't slide downhill. Graph that out as a function of the coefficient of friction, and a graph that if you ChatGPT can't do that, but the students can. And so basically give assignments that are at a cognitive level above and beyond what ChatGPT can do, showing all the work, presenting graphical representation of the results and so on, and then you really won't have a problem at all.
Yeah, I agree, and I really liked your idea about using ChatGPT for getting the wrong answers and proving that is wrong. So that's I think that's a brilliant twist in using AI. Okay, there is one more, or maybe a few more questions. And thank you very much, Anne-Marie, for sharing that link. Could you explain before we go on?
I can comment a bit. Yeah, I wrote a paper together with Bor Gregorczyk in Uppsala. Well, he said we should write something about the ChatGPT because we had quite a lot of quoting responses from it in Facebook group. So he said we should, and I said if you should write, we should do it now when it should be physics education because it should be quick. Well, they took them 3 months, so it's rather slow for them. But it's published, and we have a video abstract to go with it with some of the responses too. So you may have fun with it. We had fun writing it at least. And of course, it quickly gets outdated. I think the ChatGPT is getting better, but we got quite a lot of nonsense answers from it. We asked about if you throw something into the air, what's the acceleration in the highest point? And I'm sure you have all tried that and know what students answer. I recall once having had a group of students said, now we know it's not zero, but we don't believe it. Spending a lot of time on it, but they still didn't believe it.
Thank you.
Yeah, thanks for that link.
So maybe there's time for one more question. And someone would like advice on building confidence in stage 1 undergraduates and methods of assessment that really test understanding versus recall.
Sure. Yeah, and coming back to that question with the notion of testing understanding, that comes back to the emphasis on conceptual understanding, which is exactly the sort of thing that I was trying to address with those clicker questions. And I will include questions like that on the exams as well. So providing not just the standard sort of real problems, quote unquote, on exams, but really give them conceptual questions as well. And I'll do that either as a multiple choice or I'll do as a ranking task. And what's really nice is with the some of the older systems for grading multiple choice exams, you just had a choice of A, B, C, D, E, with the advantage of some newer systems that are out there as well. I've had a case where I've given multiple choice questions where there are 10 possible answers. And there, the likelihood that a student will get the right answer just by random guessing is negligibly small. And so, but yeah, I'm definitely up there with conceptual understanding. some of the best classes I've taught have been the very small ones, where I literally had the students do oral exams. And obviously that's not going to work with 300 students unless you're unless you have superpowers beyond anything in any comic book I've ever read. But it's certainly in small classes I've done it. Actually, one of the most amazing experiences I had, and it's not just a matter of introductory students. I did that once in a class where I was teaching graduate level electricity and magnetism. And I gave the students an oral final exam. And I don't think those students have ever sweated as hard in their life as they did on those. And it was really just conceptual questions. So I remember one of the questions I gave them was, okay, here are Maxwell's equations. What would the universe be like if that minus sign became a plus sign?
Mm-hmm. Yeah.
And they really had to think about it. So, and that was a purely conceptual question. So I agree the conceptual things are very important. And I think if you do as much of that as you can in the classroom with giving them guidance on the conceptual stuff, that will scaffold everything else going forward.
Great, thank you. And probably one more. Yes, Anne-Marie, I can see you. You want to say something?
I was just going. I certainly agree with how much more fun it is to lecture when you have this interactivity. I used colored piece of paper for a while which was easy. I gave them Greek letters and green paper and so on, so they had all these colors with them, and it was quite nice because I could also see who had answered what, so I could decide which way I wanted to take with it.
Yeah.
But of course, it didn't give me the direct feedback to give to the class, but it was quite amazing. I got these 100+ students who are usually shy. They all voted, which I was quite amazed about.
Yeah. The most amazing example I've seen of people using that technique, Ed Prather, who's an astronomy professor at the University of Arizona. He does not use any technology. I believe he just has students hold up fingers in front of their chest for whether the answer is A, B, C, D, or E. And he does that in the largest lecture hall at the University of Arizona, which has 1,200 seats. And somehow he's able to make it work. So these techniques definitely scale, and they scale to very large class sizes as well. I hope none of you have to teach classes with 1,200 students, but if you do, these techniques work there as well.
I think students appreciate a little bit of interactivity, definitely. Oh, yeah. Maybe the final question about your plans, especially with university physics, the mastering part of it. What are your plans?
Sure. And we're actually just beginning work on the 16th edition as we speak. And actually, one very cool thing we're going to add to the 16th edition is, so many students, they look at what's in a textbook and who are the people where they came up with these ideas and who scientists are. And there's this notion that basically it's a bunch of old white men. And speaking as an old white man, I agree that we want to disabuse students of that notion. So actually in every chapter of the 16th edition, there will be a sidebar about a young person who's using physics, either as a physicist or in a related field, and what their experience was with getting to where they are in physics, and what advice they will have for someone who's taking intro physics right now. And so we'll be having scientists and engineers and other folks represented there from really around the planet, different ethnicities, different genders, all that. And so it's going to be a really interesting project and really sort of opening up the world of physics and make it clear to many more people just who are the people that use physics, and the answer is it's people just like you.
Great. It's really exciting. Sounds really exciting. Well, I think we all got really valuable thoughts to take with us today, and thank you very much. I really enjoyed it, even though I'm not an expert on physics, but I always enjoy such lectures. So thank you very much, everyone, for joining and participating, and also a special thanks to Dora from Pearson in the background for your hard work. Of course, big thanks to Roger for joining and sharing your knowledge today. It's been very much appreciated. We'll be in touch with everyone after this in the form of 2 emails, one giving you information on how you can get in touch with someone from Pearson for things like a sample copy of the book, a demonstration of Pearson courseware like Mastering Physics, which the author has covered today, or a consultation if you just like to speak to someone from Pearson to hear a bit more. And then there will be a second email a bit later with a link to the recording of today's webinar. It will be it can be expected in about a week's time. So thank you all, everyone, for attending, and have a lovely afternoon.
Thanks, everyone. Mange tak.